In the beginning, all was darkness. There was no matter, only darkness. But out of this darkness came hope. Hope for the matter that would rise up and take back what belonged to it. This is its story, the story of dark matter. It was a day like any other for our young couple, Reuben and Ford. However, today would be the day that they published the most important scientific paper of all time. It was called Extended Rotation Curves of High Luminosity Spiral Galaxies. From this paper, Reuben and Ford generated the most controversial question in the entire history of astrophysics. Why do galaxies rotate this uniformly about themselves? To answer this, we go to David.
In calculating the effects of dark matter, one must look to the rotational velocities of galaxies. To do so, you would probably think it requires a relatively high level of mathematics or physics to solve, which is far beyond wrong. The trick is knowing where to look. Thanks to Dr. David Lizardi, we found that the simplest calculations would be in galaxy clusters. This is true for two reasons. Number one, the galaxies are nearly point particles in their given systems, and two, they're nearly spherically symmetrical. In considering the effective masses of the system, Dr. Lizardi also pointed out that in an approximation, any GR or SR correction would be several of orders of magnitude below what we actually would care about. That being said, great, a whiteboard with numbers and stuff on it. What we were saying about the spherical symmetry comes out in the mass distribution here. You can see that the average mass will be taken over a density function times the radius and integrated all the way across, which comes out to be some just ridiculously complicated looking junk. So what we're going to do is look at the simple introductory mathematics as to how to calculate this. So looking at that, the math is not simple. The hardest part about it is plugging in for your mass here. Now, as you can see, this graph would suggest that the innermost stars should rotate more quickly than the outermost stars. Ha! How convenient. A marker just appeared in my hand. This graph would look something like this. With this being our velocity, and this being our radius. The strange thing here is that though this calculation is correct in every way, this is not what we see. In fact, what we see is really strange. Look, conveniently placed graphs. On the top, we see what we actually calculated in MATLAB. You see that it goes as the 1 over the square root of r. Basically falls off as you would expect. As the radius increases, your velocity decreases because the force does not have to be so great. What we actually see in galaxies, though, is that the velocity increases as a function of radius. So as you travel outwards, you'll see that the velocity of these galaxy clusters will tend to increase. Not only will they increase, but at some point they will reach a flat level where the velocities are the same at almost every radius. This is pretty strange, and the only way that they can figure out how this could happen is by saying that there's extra mass that's in there, and we just don't know what that is. So we called it dark matter.
To demonstrate this, here are simulations of galaxies based on these calculations. First, we have what we would expect if there is no dark matter. The innermost stars would rotate more quickly than the outermost stars, as you can see. Next, we have the rotations that we actually observe. As you can see, they are very different. So clearly, something else must be going on.
Dark matter is defined to be the mass that makes up for the difference between what we observe and what we measure that is unobservable. The properties of this substance are still one of the most wishy-washy arguments in astrophysics because so little testing can be done upon it. Dark matter can be thought of as an answer to the question, what's in the box? We know what's in the box acts on visible matter in the same way as typical mass does, at least to a constant multiple. So we can say that what's inside the box is massive. The box, however, will not allow you to see inside or interact with its contents in any manner. Imagine, if you will, if anybody is familiar with the game of Portal, that on each side of the box is a portal that sends light from one side to the other without going through it in any way. Now imagine that the box is really tiny, but there are tons of these boxes spread uniformly throughout the galaxies. It becomes almost impossible to detect at all. individually, but as a whole their impact is visible. So we really just defined that there is some sort of something interacting with the galaxies that is, by itself, undetectable. One current theory to explain dark matter is the particles known as machos. A variation of this, Wimp's theory, predicts that there may be elementary particles that do not interact with the electromagnetic field, but are very massive, on the order of hundreds of GeVs, and interact only with the gravitational and weak nuclear forces. This gives approximately the mass needed for an explanation of dark matter. Unfortunately, there has been no detected particle in the range at which the WIMPs were expected to exist thus far, and the gap is closing quickly.
As we have seen, there must be something else going on here. Whether this mysterious force consists of small, furry animals, boxes with portals on them, or forces unknown is up for debate. You know experimentalists, when they want to measure something, they shoot it with a cathode ray gun. And if that doesn't work, it must be dark magic. One thing is certain, though. We don't know as much about the universe as we once thought, and dark matter is one of the prime suspects.